So today we are going to talk about sensitivity and specificity. So in simple words, sensitivity means the ability to detect a true positive. Specificity is ability to detect true negative. So what does that mean? If you are using a certain test to find out or detect a patient, whether that patient is suffering from that disease, if that test can actually identify a true patient and give the positive result, that is sensitivity. And if that test has the ability to figure out for a patient or a person who's not having that disease as a negative result, then it is called the specificity. So in order to have a better result for a given screening test or a certain test to figure out a disease, both the sensitivity and specificity value should be high. Okay, you cannot get 100% for both most of the time, but you can balance these two and you can come up with a good values for both sensitivity and specificity. So if a test can identify actual patients and give a positive result and non-patient and give a negative result with a very high percentage, then we call that test is a good one or an effective one. Okay. And then we have something called the Ppv, that is the positive predictive value. That is the probability that the people with a positive screening test result indeed do suffer from the illness. So this is like the other way around of the sensitivity. And then we have the negative predictive value. That is the probability that people with negative screening result indeed do not suffer from the illness. So that is again like the reverse of the specificity. Now in order to do the calculations or to show you how this sensitivity and specificity is conducted or calculated, let's use this contingency table. So you see a 2x2 table here. The columns you have the truth, okay, they actually whether that person is suffering from the disease or is not suffering from the disease. Then after they undergo the test, whatever the screening test, whether they got the positive result or the negative result. So those information will be included in this 2x2 table. And then you can get the column sums, the row sums and the grand total here. Okay. So let's say that, okay, now let's try to figure out what these 4 cells are representing, right? If the patient or a person is actually suffering from the disease, so that is the first column, right? If the patient is actually suffering from the disease. And then the test also gave the positive result. So that is called a true positive, right? You can understand that. This is the true positive. In the same manner, if the person is not suffering from the disease, that is the truth. So this column. And the test also gave the negative result. Okay. So the person is not suffering from the disease, so the test should give negative result if the test is correct. So that is called a true negative. Okay. So this cell is called the true negative. Now you can guess what are the other cells. If the patient is actually having the disease, but the test giving negative, what does that mean? That is a false negative. So this column is, this cell is the false negative, and in the same manner, if the person is not suffering from the disease and the test results give positive, so this cell is the false positive. Okay. So you have true positive, true negative, false positive, and false negative. Now I'm going to name these cells as A, B, C, and D. Okay. So I have named these 4 cells as A, B, and C, D. Now let's try to find the row sums and the column sums. So if you go over the first row, the first row sum is A plus B. The second row sum is C plus D. First column sum is A plus C. Second column sum is B plus D. And then the grand total will be A plus B plus C plus D. Either it can be from the raw totals, or either it can be from the column totals. Okay. Now let's try to find how to get the sensitivity. Okay. So these are the four measurements: sensitivity, specificity, Ppv, and Npv. And in addition to that, you can calculate the disease prevalence also. Okay. So the disease prevalence means out of the total population or the sample, actually how many are suffering from the disease. Now, if you look at this table, where can you find the total for the sample or for the population? Where's the total? So the grand total, that is the total. Okay. So out of everybody, how many are there actually suffering from the disease? How many are there actually suffering from the disease? Using these A, B, C, D values, can you find that number? A plus B plus C plus D is the total, everybody. Out of them, how many, what is the number of people who are actually suffering from the disease? Can someone find that value? So first find the whether these are the columns or the rows which contains the real world scenario. Is it the columns or the rows? Actually, what's happening in the real world? Those are the columns, right? So in those columns, which is the column that shows you who's suffering from the disease? I think I got one answer. A plus C, yes. So A plus C is the number of people who are actually suffering from the disease. So the disease prevalence or the prevalence of the disease is A plus C out of the total, which is A plus B plus C plus D. So you can easily find that. Now, what is the sensitivity? Sensitivity is the ability to detect the true positive. Okay. So what does that mean? Among those who have the disease, okay, among those who have the disease, if the test results can give you the positive, now that is the probability of giving a true positive. Okay. So you can write this as the probability, okay, the probability of giving positive, knowing that they have the disease actually. Okay, so in the real world, they have the disease. So what is the probability that the test can give positive, knowing that this person has the disease? So this is the conditional probability. How do you find it? You need the intersection, that is the positive and disease. You divide by the given one, which is the probability of the disease. So how do you find that? Okay, you have the positive and disease is A, that is the true positive. You divide it by the probability of disease, or in actually if you look at this table, it will be A divided by A plus C. Okay. So the total A plus B plus C plus D, it is cancelled out top and bottom. So at the end you can get. So this is the conditional probability. You restrict your sample to, you already know that they have the disease. So the total is only A plus C. Out of them, you get the positive result for the test, that is A. So the sensitivity is A divided by A plus C. Okay. Or simply those who get the positive result among those who actually have the disease. In the same manner, you can find the specificity, that will be giving a negative result, knowing that these people are not suffering from the disease, right? So again, in the same manner, you can apply the conditional probability. If you look at the table, that will be D divided by B plus D, right? Usually the sensitivity and specificity are given as percentages. So you can multiply this by 100%. Okay, so you can get the percentage value. Okay, even the disease prevalence, you can represent it as a percentage. Okay, is this clear to all of you how to get the sensitivity and specificity? Now do not try to memorize these ABCDs, okay? Get the idea. Okay, the idea is giving a positive test result for those who actually have the disease. Okay, that is sensitivity. Specificity is giving a negative result for the test for those who are actually non-disease, right? So if you can understand that, you can easily find this probability or these numbers, okay? Because if you get the table, the columns and the rows the other way around, sometimes you may end up with, and the positives, negatives, the top bottoms, you won't get the same ABCDs, okay? So therefore, do not try to memorize these ABCDs, okay? Get the actual idea, okay? Understand actually what is the meaning of sensitivity and specificity. Then you can easily answer these questions, right? So what is the PPV? PPV is probability that the people with positive test result indeed do suffer from the disease. So out of those who have the positive result, that is the given one. Indeed, they have the disease. So how do you find that? Disease given positive. So it is actually the other way around of sensitivity. How do you find that? Okay. So that will be, so you already know they are the positive. So this is the first row. You have total A plus B. Out of them, actually this is A. So the PPV will be A divided by A plus B. In the same manner, NPV will be the probability non-disease given the test result was negative, right? So the negative is the second row. So we have C plus D, right? C plus D is here. Out of them, you got the negative results. Out of them, the non-diseases are only D. So the answer will be D divided by D plus C. Okay, so this is how you find sensitivity, specificity, PPV and NPV. Okay, right. So let's try to do an exact example and see whether you can understand and answer these questions. Okay, so I'm going to write a small example. This example, we have 4,810 expecting moms. They underwent a screening test. So this test is to find out whether their baby is carrying Down syndrome, whether they are likely to be carrying fetus with Down syndrome. Okay, so in this sample, and after they were then followed until they deliver the baby, and then they recorded whether the baby is healthy or suffering from this syndrome. Okay. So what they want to check is whether the screening test is actually giving the correct result. Right, so let's see what are the numbers they got. Okay. So I'm going to draw the table now. Let's try to draw it nicely. So here's the truth. So after they gave birth, we can record affected baby or non-affected. And then the rows are the screening test. So that whether the test gave positive or negative, right? So here are the numbers. So we have the total of how many? 4,810. Out of them, only 10 babies had the syndrome. All the other 4,800 were healthy babies. And these are the test results. Okay, so if you look at these figures, what is this 9 means? The test gave the positive result and the baby was also suffering from the Down syndrome. And this 4,449 is the baby is healthy and the screening test also gave negative. So 9 is the true positive, 4,449 is the true negative. And you can find these row sums also. So 351 plus 9 is 360. And this will be 4,450. Okay, now let's try to find the disease prevalence, sensitivity, specificity, Ppv and Npv. Okay, so you can also try the disease prevalence. Okay, so that will be how many actually suffer out of the total. So we know that there are 4,810 babies. So I think, so in this one, we assume all births were okay, no deaths occurred, okay? So 10 out of 4,810, right? What is the sensitivity? Out of those who actually suffer from the disease, the test gave positive for 9. So what is the sensitivity? So this is 90%. So 90% sensitivity for a screening test is a very good result. Okay, then let's check the specificity. Specificity is giving negative for healthy. So healthy is 4,800. Out of them, correctly identified 4,449 as negative. So can you find this percentage and tell me the value? 1 decimal place will be enough. Okay, so we have 92.6, yes, 68. So let's say 92.7. Okay. So this is 92.7. So you can see that both sensitivity and specificity are very high numbers. So that means this screening test is a good one. Now, sometimes you can get sensitivity about 95, 96%, but specificity becomes very low, 60, 70, even 50. Okay, although the test can correctly identify positives or true patients, they fail to identify non-patients. So that is not good. Okay, so both sensitivity and specificity should be balanced. Even 85 for both, above 80 for both is also okay. Okay, sometimes the sensitivity is very high, but not the specificity, or the other way around. So that is also not good. So this one is a good one actually. So this 90%, if you want to explain it in your words, what does that mean? 90%. Okay. So if you interpret, usually after you calculate this sensitivity, specificity, NPV and PPV, interpret it. Okay, because anybody can just get the figures, look at the table and calculate them. But when you do statistics, you have to interpret your results. Okay, so tell the usual audience what is actually the meaning of this sensitivity. So what is this, the 90% means? The test has 90% accuracy to detect actual patients. And then the test has 92.7 accuracy to detect actual non-patients. Okay, or you can say the ability to detect a true positive is 90%, ability to detect a true negative is 92.7%, right? So that is also okay. Now, can you find the Ppv and Npv? That is Ppv. That is the probability this is given positive. Okay, so given positive is you have 360, out of them there are 9. Okay, so find this also. And then the Npv. Npv is no disease given negative. So that will be 4449 out of 4450. Right. So find these percentages also. Okay, so the Ppv is 2.5%, correct? What is the Npv? 99.97. Okay, so thanks for the answers, correct? So this is 2.5%, which is actually 0.025. And this was 0.999, so let's say 99.9%. Now, according to the context, how do you explain this 2.5%? If a mother screens positive, there is 2.5% chance or probability that she's carrying a affected baby. Affected fetus. Right? Now you can write in the same manner what is NPV if a mother screens negative. There is 99.9% chance that she's carrying a healthy baby. Okay, so for any test, you can do the sensitivity and specificity calculations using a proper sample, okay, or for a population. Okay, so is this clear to all of you? This is prevalence, sensitivity, specificity, NPV and Ppv. Any questions? So maybe you have heard these terms earlier and now you know how to interpret them and exactly what is the meaning when you say a rapid antigen test is 60% sensitivity and 70% specificity. Actually, what does that mean? Now you know. Okay, right. Shall we try another example? Okay, so this is for you to try. You have to prepare the table for this one also, okay? In a clinic of 2,000 registered patients, 1,250 are suffering from, let's say, diabetic. According to certain screening test, and then 28 negative results for non-diabetic. Okay, so the total sample is 2,000. Out of them, there were 1,250 diabetic. Among those diabetic patients, for a certain test, 160 got positive, the rest negative result. And among those who do not have the diabetic, 28 got negative results. Okay. Now prepare the table. And can you calculate disease prevalence, sensitivity, and specificity of the test? And also Ppv and Npv. Okay, so all 5 calculations. So when we say disease prevalence here, that is for these, among these, for this clinic, the disease prevalence is, that is for the diabetic. Okay, among these 200 patients, what is the prevalence for diabetic? Okay, can you formulate the table and then calculate these values? I'll give you 10 minutes. Okay, try it yourself. And if you have any questions, please speak up. Okay, I think I got a few of the answers. Okay, so I have the table now. See whether you have the same thing with you. Okay, were you able to get this table? With so you have 2000, and if there are 1250 diabetic patients, we have only 750 non-diabetic patients. So we have the positive results 1160. So in order to get the column total 1 to 50, you need 90 for negative. Okay, and so on. You can fill the rest. Okay, I got several correct answers, I think. Right. So what is the disease prevalence? 1250 divided by 2000. You can find it. Yeah. Specificity, right. Sensitivity is very high, which is 92.8%. And the specificity is, well, that is very low, which is 61 point, 3 point. 3.73. And then the Ppv was 61.63, and Npv is 28/118. Which is 23.73%. Okay, so any different answers than this? Please tell me. I think those are the answers I got from you also. Yes. Okay, do you need more time, or I hope you are done now? Right. Then you have to interpret them. The sensitivity 92.8% is what? The test has the ability, 92.8% ability to detect a patient correctly. but it has only 3.73 ability to detect a non-patient correctly. So specificity is very low, although sensitivity is high. So we cannot say that this test is actually a good one. Okay. Although it can identify patients, it's poor in identifying non-patients. Giving negative for non-patients, it's very poor. So therefore, the Ppv, that means if a patient got positive result, he has 61.63% of chance that he has the disease. And then if a person got negative result, that person has 23.73% of chance that actually having the disease, right? So make sure you know how to interpret these 4 results also, okay? And what is the disease prevalence? The chance of having, the chance of being a diabetic patient in this clinic is whatever the disease prevalence, okay? Right. Any questions so far? Usually okay, so about I have a question about in a test, should both Ppv and Npv very high to be good study? Usually when we check the quality of results, we only look at sensitivity and specificity. Because if the sensitivity and specificity are higher, you should automatically the Ppv and Npv also gets higher. Okay. Therefore, we do not use those figures to check the effectiveness of a test. Only the sensitivity and specificity. Ppv and Npv are used just to get an idea about about the population, what will happen if you got a positive result, what is the probability that actually is a patient, things like that. But usually to get an idea about the effectiveness of the test, we only use sensitivity and specificity. Okay. This Ppv and Npv are used to get an idea about the population or the sample usually. Okay. Right. Any other question? So usually if sensitivity and specificity are good, Ppv and Npv are also, they have the same relationship. Okay. Okay, then. So that is about the last topic, sensitivity and specificity. So I hope you will be able to calculate these values given a certain scenario and numbers, and know how to formulate the table. Okay. So I'm going to unshare the screen now and share the screen for the next topic. Okay, so we are going to start chapter 4, again related to probability, but now we are looking at some probability distributions and probability densities. Okay, now we know how to calculate probabilities, right? But usually when you look at the behavior of certain random variables, you need a function to define the behavior of those random variables. You cannot always calculate the probabilities in usual manner, find in the event sample space and so on. So therefore, by looking at the usual characteristics or behaviors of certain random variables, there are distributions defined for random variables. Okay, so you know what is a random variable now. You know a random experiment. So any measurement that you take in a random experiment, they are the random variables. So you can see what a random variable is in this definition. For a sample space S with the probability X, for a certain function, if you can find the values for that probabilities, the values that you have in that sample space X, then we called X as a random variable. So simply, if you think about an experiment about measuring the pH value of water samples, that measurement pH value is a random variable because from one observation or one sample to another sample, that pH value is going to change. So it is a variable. Another example, if you think about a class of 100 students, you measure their height and weight. Height and weight, those are random variables because the value is changing from one student to another student. Okay, it is it's varying, the variable. Okay. And then by looking at the behavior of these measurements, say for example, you have exam scores of 100 students in a class. So your random variable is exam score because the score is going to be different from one student to another. After you collect these exam scores, you can draw a small graph. You know now how to draw graphs, a stem and leaf diagram or a histogram or maybe a dot plot. You can look at the shape, right? Maybe it is symmetric, maybe it is not. Maybe there are outliers. You can find whether there are several peaks or only one peak, that is unimodal or bimodal, multimodal. You can find those type of things, okay? So those features, if you think about them together, we call it the distribution of that random variable, okay? So if you can find how each and every score is available for that random variable, or let's say the chance that a certain value can be allocated for this random variable, and if you can figure out the probability of occurrence of that value for this random variable, we call it the probability distribution. Now you already know the total probability is 1. Okay, you know the total probability is 1 for a certain sample space. So that sample space contains all possible outcomes, right? So for a given experiment, if you can write down all possible outcomes in that sample space and the chance of occurrence for all those possible outcomes, then you can say that is the probability distribution for that random variable. Now, if you cannot understand yet, I'll show it using this simple example. Think about rolling a balanced 6-sided dice. Now, you already know this experiment. You have a 6-sided dice. It's a balanced one. That means all 6 sides, they have the same chance to give the result, right? Now, if you can write down its sample space, you already know it is 1, 2, 3, 4, 5, and 6. Okay, if you roll this, let's say 100 times, and you can note down, okay, out of this 100, how many ones are there? How many twos are there? How many threes, fours, fives, and six, and so on? You can find the probability, right? Out of 100, how many ones in a percentage? Out of 100, how many twos, and so on, okay? Now, we know by this law of large numbers and by experience, since it is a balanced die, all these possible outcomes has the same chance of being selected, okay? That means the total probability 1 is equally divided among or equally distributed among all possible outcomes. Among all x's. Now, what are our x's? X can be either 1, 2, 3, 4, 5, or 6. And by experience, we know the probability of giving 1 is 1 over 6, 2 is 1 over 6, 3, 1 over 6, 4, 1 over 6, and so on. Okay, so this is from the law of large numbers. If you do this many times, you will end up with this probability chart. So this is called the probability distribution of the random variable x. So what is our x? The outcome of rolling a balanced 6-sided dice. Okay, x is the outcome of rolling a 6-sided dice. So what do you see in this small table? For whatever that random experiment, the random variable is x. Its all possible outcomes are listed and their corresponding probabilities. Okay, so simply, if you can note down all the values in your sample space, that means the possible x's, okay, the possible values for your x, and then their corresponding probabilities in a small table like this. So we call it the probability distribution of x. right? So when your X is, now you know your random variables can be discrete or continuous. You already, now you know that, right? What is the difference? The discrete is where you can have whole numbers like number of students, a number of vehicles in a parking lot, and so on. No fractions, no decimals. Then you have continuous variables like height, weight, temperature, rainfall, where you can have decimal values and fractions like 27.5 degrees Celsius or 125.75 kilograms. Those are continuous variables. So depending on whether your random variable is discrete or continuous, for these probability distributions, we use two different names. If it is discrete, we call it the probability mass function. So I'm using this notation, okay? Prob means probability mass, Fn is for function, or simply PMF. If the random variable is continuous, like exam scores, height, weight, rainfall, and so on, we call it the probability density function. Just two names, okay? It's the same thing, but just to differentiate between discrete and continuous. So, okay, so let's look at the PMF first, and later we'll move on to the continuous, okay? So you need the knowledge about these distribution functions, because in your research work or when you gather data, you will end up with categorical variables, discrete variables, continuous variables, and you have to interpret these variables, how they are behaving, right? So, and sometimes calculate probabilities. In order to do that, you should have a knowledge about the distribution of these random variables, or how the total probability one is distributed among its possible outcomes. If you know that pattern, then it's very easy to find the averages, variances, and then calculating probabilities and even getting an idea about the shape of your random variable, okay? Especially when you talk about the normal distribution or the Z scores, you should know this, the idea behind the probability distribution. So that is why we included this one in your curriculum, okay? So here's a difference example, 4.2, and we are going to use this example throughout this discussion, okay? So example 4.2. In a sample of 50 households, 10 families has 2 members, 15 had 3, 12 had 4, 8 had 5, and the rest had 6 members. Okay, so your sample is a small sample, 50. Out of that 50, 10 families had 2 members, 15 3, 12 4, 8 5, and the rest had 6 members. We have to list the elements in this sample space and their corresponding probabilities. So what is your element X? The random variable X is the number of members in a family. Okay, so the first thing, identify what are the possible values of X, or actually your sample space. Okay, what are the possible values of X? Okay, so let's go over the context again. What is your X? Number of members in a family. So it says 10 families had 2 members. Okay, so it can be 2. 15 had 3 members, or X can be 3. Then you have 4 members, 5 members, 6 members. So what are the possible values of X? 2, 3, 4, 5, and 6. So in this sample, there are no families with more than 6 members. Okay. And you know, if you need a family, at least 2 members should be there, right? One individual, you cannot say it is a family there, right? So actually it's 2. Now let's try to find the probabilities. How do you do that? Okay, so we'll prepare the table. X and Px. If you want, you can do it vertically or horizontally, right? So X and Px. So what are the possible values of X? 2, 3, 4, 5, and 6. Now let's find the probabilities. So total 50. Out of them, 10 had 2 families, 2 members. How do you write it? 10 divided by 50. So that is the probability. You can find it, right? 3 members, 15 families out of 50. Then 4 members, 12 families out of 50. 8 families out of 55 members, and the rest, you have to find the rest. How do you find the rest? The total should be 50, right? So there are 10 plus 15, 25. 12 and 8, 20. So 25 and 20 is 45. The rest is only 5. Okay. Now can you find these probabilities? That will be your probability density function. Okay. So what is 10 over 50? 0.2. 15 over 50 is 0.3. 12 over 50 is 0.24. This is 0.16. This is 0.1. Okay. This is the probability mass function of your random variable x. So it's very simple. You identify all possible outcomes and write down its probability in front of it as a small table. So you get the PMF of x. Is this clear to all of you? Any questions? Okay. So you see that x is a discrete. You cannot have 2.5 members in a family, right? It's not possible, right? So these are whole numbers. So this is a discrete case. So you have the discrete random variable. You already saw this example. Variables define our discrete sample space. So these are the whole numbers. Okay, so those are the discrete random variables. Okay. Now, when you prepare this discrete random variable, the PMF, right? So here's the probability mass function PMF. There are two conditions that you have to satisfy. Okay, there are two conditions that you must satisfy in order to be your function or that table a proper PMF. Okay, so we call it a legitimate PMF or proper PMF. Legitimate PMF, all right? Because you can prepare tables like that. Okay, but only if these two conditions are satisfied, then we say it is the PMF of x. So what are those two conditions? All the probability values should be greater than or equal to 0. You cannot have negative values. That's obvious because these are probabilities. And then if you add up these px's, they should add up to 1. This is the total probability. Again, this is obvious because your probability distribution or PMF is actually what? That shows how the total probability 1 is distributed among the all possible outcomes. So if you add these values, it should add up to 1, right? So let's check it, okay? So let's use the same example. I'll write the PMF again. Two, three, 4, 5, 6 corresponding probabilities. Better to have it with 2 decimal places. Okay, so let's see whether these two conditions are satisfied. So look at all the px's. You can see all of them are greater than or equal to 0. No, zeros actually, all of them are positive. No negative values. So first condition is okay. Now let's add these values together. Okay, so you have 6, 8, 9, 10. So if you sum up all the px's for all possible x's, that is 1. So that condition is also satisfied. So this PMF is a valid. This PMF is a valid probability mass function. Okay. Okay. So by looking at a PMF, you should be able to check and double check and verify. Okay. So this is actually a probability distribution. Okay. Because anyone can prepare tables with possible x's and probabilities, but only if these two conditions are satisfied, we say it is the PMF or the correct PMF of that random variable x. Okay. Now let's see how we can represent this in a graph, right? So what do we have? We have probabilities and now this is discrete. Okay, so remember you are dealing with the discrete random variables. So let's put a tick. 1, 2, 3, 4, 5, 6, 7. And let's write down the probabilities in the y-axis. So these are the px's. Okay. If you look at the outcome, the highest is 0.24. The lowest is 0.1. Anyway, let's divide this into 0.25, and it goes on up to 1. Okay, the maximum that px can get is 1, right? So that's the total probability, and it goes. So I'll stop from here. Now let's try to draw this one. Now remember, this is discrete. So in between 1 and 2, if you look at the values in between the interval 1 and 2, there's nothing. Okay, this is discrete. 2 and 3, yeah, there should be nothing. Okay, only at exact value 1, you have a certain probability. Now, according to this one, 0 and 1, we don't have any probability, so you don't have to do anything. But for 2, you have probability 0.2. So we draw a small line up to probability 2. Okay, then 3, it is probability is 3. So here's 3, right? Okay. Then 4 is 0.24, somewhere over here. Then 5 is 0.16. 6 is 0.1. So here's the graphical interpretation of the above PMF. Okay, remember you cannot connect these. Okay, you do not have bars or anything. Why? Because in between 2 and 3, 3 and 4, in between these values, there are nothing. Okay, these are discrete. You don't have 2.1s, 2.2s or anything. They don't have any probability. Only 2 has probability 0.2. Then you jump. Only 3 has probability 0.3. In betweens, there's nothing. Right? So therefore, you cannot connect no bars, no columns, nothing, just a small straight line. Okay, so this is how you interpret the PMF, right? Because this is discrete. When it comes to continuous, it is different. Okay, right. Now then we can find something called the cumulative density function. So when you say cumulative, that means you add continuously to the next one, right? So it is very easy. If I use the same example and show it other than showing it using these equations. Okay, so don't worry about the equations. I'll show you how to get the CDF, the same example. Okay, here's my x and px, 2, 3, 4, 5, 6, 0.20, 0.3, 0.24, 0.16, and 0.1. The cumulative distribution, we denote it as capital Fx usually, right? So how do you write it? What you do is you add. See, you add each and every value to the one above. So 0.2 is the first one, you leave it there. Then you come to the next one, you add 0.2 and 0.3. You add them together. What do you get? 0.5. Then you add this 0.5 to the next one, 0.25. What do you get? 0.74. Then you add it to the next level. 0.74 plus 0.16 is 0.90. And finally, the last one, 0.9 and 0.1, you get the total probability 1 at the end. So this column Fx, that is your CDF. Okay, what do? You continuously add. Each row you add to the previous one. So you add them together cumulatively. Okay, so that is the idea. And at the end, you attain the total probability. Okay. And we can draw it using a graph. Okay. 1, 2, 3, 4, 5, 6, and it goes on. Okay. Now this is going to be different. This is the capital Fx. Okay. Now before 2, you don't see any probability. Okay. Starting from 2, you have this probability 0.2. In other places, it is 0. So you simply draw at the 0. Okay. It's 0. It goes up to negative infinity, and this goes up to positive infinity, right? Okay. At 2, you jump to the probability 0.2. Okay. And then it remains at 0.2 until you come to the value 3. Right. And at 3, you attain the cumulative probability. What is it? 0.5. So you jump it. Right. So it is a jump. Now remember, you don't color this the circle at 3 for 0.2 because it attained 0.5. So that is a jump, right? And then it will remain there up to 4. And at 4, it attains, what is the next probability? 0.74. So then it jumped up to 0.74 and remains there until 5 jumps up to what? At 5, it is 0.9. Okay, and then remains up to 6. At 6, it attains the total probability 1. Okay, and then there's nothing more to obtain. Okay, it remains there up to the whatever the values you have for x. You cannot add any more probability because it has reached its maximum. Therefore, for whatever the values after 6, it will remain at total probability 1. Okay, you can't jump anymore. That's the maximum you can go, right? So you can see that the CDF is a step function. Okay, because see, it's like a step jumping up and up. Okay, so this is to give you an idea about how these cumulative densities are working and the probabilities are working. Okay. Now, in addition to identifying the behavior, you can find probabilities. Okay, so you have the PMF of X. What is X? The number of members in a family. Now let's try to answer some questions with the probability. Right. So what is the now this sample 50? Let's say this 50 sample of household is taken from to represent a certain village. Okay. Now you can make some guesses about the probability distribution of number of members in a family for that village based on our sample. Okay, so again, you have a certain village. There are a lot of households. You select only 50 in your sample. Okay, you know there are several ways to select. You know the sampling techniques now. Suppose randomly you select 50 households. For that 50, the number of members, that distribution is there. Okay, you have this distribution. Based on this distribution, you can make some predictions or inferences about the behavior of the number of members in a family for this whole village. So that is just an estimate or a probability or a chance. So you can say the probability that a family in this village, family has only 3 members. What is that probability? You simply look at the table. What is it? 30%. Okay. So based on that sample, you say in this village, okay, you can assume that 30% of members or families have only 3 members. Or you can find something like, so our X, okay, I'm going to use the notation now. Now, what is this? This is probability X equals 3, exactly 3. But if you want X greater than or equal to, let's start with less than or equal to 3. How do you find that? X less than or equal to 3. What are the possible values? X can be 3, so it is less than, and X can be 2. So these are the possibilities where X can be less than or equal to 3. So what are those probabilities? You have them, 0.2 and 0.3. Add them together, and you already have it in the FX. So this is 0.5. So you can easily find them from the table. Another one, what is the probability that X is greater than or equal to 5? So what are the possibilities? Equal sign is there, so X can be 5, greater than, X can be 6, that's all. What are those probabilities? 0.16 and 0.10. So that is 0.26 or 26%. Okay. Try this one. What is the probability that randomly selected family has members in this range? 3 to 5, including 5. Right? So if you want to find this probability, What are the possible values of x? Yes. What are the values that you have to add? Any answers? Okay, so I got the answer 40%. How do you get that? Can you add 3? No, 3 is not included. You don't see equal sign. So you have to start with 4. X equals 4 plus px equals 5. That's all. So that will be 0.24 plus 0.16, which is 0.4 or 40%. Okay. Is this clear to all of you? So the cumulative density is always x less than or equal to a certain x. See, okay, I'll go back to the definition of C. Probability that x is less than or equal to any x, that is fx. Okay, so if you look at this example, px less than or equal to 3, this is exactly f3 according to the definition. And see, you have 0.5. So if you use that notation, can you tell me what is f5? F5 is what? Probability x is less than or equal to this 5. That means you have to add everything up to 5 from the beginning, right? So if you want, you can do the longer way by adding 2, 3, 4, and 5, or it is straight away there in your CDF, that is 0.9. Okay. Now, what is x greater than 5? Probability x greater than 5. How do you find that? Any shortcuts that you can remember? Any shortcuts for px greater than 5 rather than using the table? You have x less than or equal to 5. Now you need x greater than 5. What is the concept that you can use? Yes. Okay, so thanks. Got the answer. What's your name? Your name is not showing. Okay, so you do the complement. Yes, thank you for the answer. You do the complement. What is the complement? This is 1 minus F5 actually, or 1 minus, or the complement. So 1 minus 0.9 is 0.01. And well, it is there. Okay, Px greater than 5 is exactly Px equals 6. But if you compare it with the previous answer, they are the complements of each other. So you do the 1 minus. Okay. So there are several ways you can apply the things you have learned in probability, even in situations like this. Okay. So another example, what is F4? That is the probability a randomly selected family has family members less than or equal to 4. Right? So either you can add 2, 3, and 4 together, or it is automatically there in the graph, the table, that is 0.74. Right? And you can find the complement. More than 4 is 1 minus 0.74. That is 5 and 6 added together. Okay. Right. So now I suppose you know you can figure out how to prepare the PMF by looking at the scenario, identifying possible x's, and then list down their corresponding probabilities in front of it. That table will be your PMF. Make sure you check the conditions. All these px's should be greater than or equal to 0. And when you add all these px's, they should add up to total probability 1. And if you want, you can construct the CDF also by cumulatively adding all the rows together until the end. And then if you want, you can calculate probabilities by looking at this table. Okay. Right. The next thing that we can find using a PMF like this is the expected value of X. So expected value is another term for the average or the mean. Okay, so the mean value. Okay, you know how to find the mean. Okay, that is X bar, sum of Xi divided by N, right? Now, when you have a distribution like this in a table, there's another simple way that you can calculate the mean or the average, or usually with the distribution, we use the word expected value, EX, okay? So how do you find the EX? You multiply X with its corresponding PX for all possible X's, right? And then add them together. See, you have X, you have its corresponding PX. Multiply them together, X times PX for all possible X's. And then add them together, you get the mean. So it's very easy. Okay, so let's try the same example. So we already have our table here. Okay, I'll write the expected value. That is the sum of X times PX. Now remember, here you have simple X, okay? Simple X means the values you can get for X. Here the capital X, this is the random variable. Simple X is the value that the capital X can hold, right? So capital X is the variable, the values that it can hold, that means 2, 3, 4, 5, 6, those are simple X's, right? So let's try to find them one by one, okay? So you have 2 times its probability is 0.2 plus 3 times its probability is 0.3, 4 times its probability is 0.24, 5 times its probability is 0.16, 6 times its probability 10. The summation means this addition. So you add them together. So let's try to find this one. This is 0.4, 0.9, 0.96, 0.8, 0.6. Now add them together and find the expectation or the mean value. Okay, who can find the answer? Okay, so we got 3.66. I guess everybody can get this answer. Any different answers? Is this correct? Yeah, I hope so. Okay, so that is how you find the mean value. So what does that mean? If you take on average, the number of members for a family is 3.66. Now, don't get confused. The mean, the value can hold any number, whether it is discrete or continuous. Your random variable is discrete or continuous. Okay, these are averages on average based on a sample. Okay, therefore, expected values, even for discrete cases, you can end up with fractions or decimals. That is okay, right? You can have such values. Right. The next is the variance or the standard deviation, right? That gives you an idea about how the data points are gathered around, whether it is close to mean or far away from the mean. You know the idea about standard deviation. Okay, so for this data also, you can find the variance and the standard deviation. So how do you find it? You can use the computational formula. You don't have to memorize them. Okay. These equations will be given to you in exams, so don't worry about memorizing them. Okay. So how do you find the variance? You need the expected value of x square. Okay, so now this is different. What is the next one? Ex whole thing square. Ex you already know. See, Ex you found it, 3.66. So this part you already know. Just square it, you are done. But you need Ex square. So how do you find it? Right? So this is how you do it. Again, we have our x's and px's. So let's find Ex square. It's very simple. If for Ex it is x times px, for x square it will be x square times px for all possible x's. If you have x to the power 3, you multiply px by x to the power 3. Okay, so it's like that. Whatever you have here, you multiply px with that one. If you have 3x, you multiply px with 3x. Okay, so it's a feature of the mean. Okay, so how do you do that? X square, it is 2 square times 0.2 plus 3 square times 0.3. 4 square times, what was it, 0.24. 5 square times 0.16, and finally 6 square times 0.1. So what do you get? 4 times 0.2, 9 times 0.3, 16 times 0.24, 25 times 0.16, and finally 36 times 0.1. Right? Now can you find this value for me? So please find Ex square, then later we'll calculate Vx, the variance. Okay. 11.1. Any other different answers? Okay, please share your answers so you can double check the results. Anybody who want to share the answer? 14.94. So that's different. 17.1. Another different answer. 14.9 for two answers. Please double check your answers and let's see. Okay, so I also got 14.94, so I guess that's the correct one. 14.94. Okay, yes. Yeah, so this is 14.94. Now let's calculate the variance of x. Ex square, we have 14.94. Ex is 3.66. You have to square it. And then you can get the variance. Can you find that also? $1.54. Yes, that's the answer. Right. So this should give you 1.54. And remember, I hope you can remember the characteristics of variance. Variance cannot be negative. Okay. So after you get the answer for variance, always check the value. If you get a negative value here, that means your calculations are wrong somewhere. This should be always positive. Okay, it should be always positive. And what is the standard deviation then? Standard deviation of x is the positive square root of 1.54. You can find it. Okay, right. So this is how you find the variability and the average of a given discrete random variable when you have a PMF. Okay, right. So here's an example for you. Any questions so far before we go to the next example? Okay, good. So let's do the next one. I would like to do this as a group work. I'm not going to grade it, just to make a difference. So all of you are just doing things individually. So let's try to do this as a group work. Okay. I'm not going to grade it, right? So don't worry. So I'm going to break up you to breakout rooms. We have 40 participants. Let's see. I'll make 6 breakup rooms. I'm going to break you break out you into 6 rooms. Okay, you will get an invitation to join. You know how to do that now. Okay. Now you got the invitation. Please join. Okay, I'm in room 1, right? Can you hear me? Anybody in room 1? Can you hear me? Rajita, can you hear me?
Yes,
Okay,
madam.
do you see the shared screen?
No,
You don't have the example? Okay, can you see the example now? Okay, please note it down. Okay, please note it down and I'll check whether others can see it. I think I'm in room 2. Can you hear me? Can you all hear me?
Yes, madam.
Okay, so do you have the question? Can you see the shared screen? No?
No, madam.
Okay, so I'm going to share it, note it down, okay? Because I may go to the other room and I want to share it with them also, okay? So I'm going to share it now.
Okay, madam.
Okay, can you see now?
Yes, madam.
Okay, so note it down quickly. One of you in your group, okay? Right, so I'm going to leave to another room. Okay, I think I'm in room 3. Can you all hear me?
Yes, madam.
Do you see the shared screen? Do you have the question with you? Anybody of your group?
Yes, madam, we have.
Okay. So why don't you talk with each other, unmute and chat with your friends, do the work. Okay.